Hello everyone, good morning. Welcome to the workshop of finite element analysis. And I'm here. We have seen EV Rapid Force from a startup company, and let's start this finite element analysis. In finite element analysis, we have seen that the full structural of vehicle. It's a chassis, BIW chassis, in which we have seen the deformation crash analysis of the frontal crash analysis. After crashing, there is some deformation or stress will be distributed in the different parts of the body. We have seen in which area or in which section more stress will be there or deformation will be there, that's we have seen. Similarly, we have just start the finite element analysis to understand the finite element analysis what we can do in future. But let's say start with basics of finite element analysis, how is to one work and how it will be solve the equations, and how we make the formation of equations, all these questions. Before this, I have introduced myself. My name is Shivam Singh, as the founder and CEO of EV Rapid Force, and also e-mobility, providing the e-mobility solution. And my qualification holds a master's degree in automobile engineering with design and development in hybrid and electric vehicle technology. As you have seen, I have a 20 plus certification in Ansys, and also holding Ansys Associate Engineer Certificate in Heat Transfer and for the thermal and structural simulation. For the certificate, recently I got the certificate of appreciation by Atmiya University, Gujarat, to conduct the faculty development program in electric vehicle technology. And I am also certified EV trainer in by the Automotive Skill Development Council. And similarly, you seen my startup company first is started in my university. That's Lovely Professional University. That's all about me. Let's start the finite element module wise. Here we have discussed in this course, in this workshop, in basically in two different module. In the first module, we have seen the introduction of finite element analysis and how to what are the methods to solving the finite element. And in second module, we have seen the practical case study of finite element, how we can solve the finite element methods, and what is the steps to follow the finite element solving in the practical in Ansys Workbench. And in the first module, we have a sub two different sub modules. First, take the methods, how to solve the methods in finite element methods. And we have seen one example of a solid bar element, in which two bar element we have a with different diameters. Two bar is connected and applying different boundary condition and gave the results we have seen in above. Before this simulation, we have just understand about the FEA. What is FEA? FEA is nothing but it's a finite element analysis, and it is the basically numerical methods to solve the solution to get the approximate and solution of some mathematical equation, just like a linear programming and differential equation. That kind of things will be doing is. Before this, we have done discretization in the system into multiple parts in a small element section, that is known as discretization. And this is very useful behavior of each element, find out the behavior of each element related to one another, to identify the whole geometry behaviors. And we have find out the different governing equations to find out the behavior of individual elements, as well as making a matrix, large matrix, to solve represent this entire matrix, how to represent this matrix, and how to solve this matrix there. And after that we have what are the finite element equation will be there, how to combine these equations. We have seen in the solid mechanics, we have seen the axial loaded elastic bar is there. For axial elastic bar, we have a equations, governing equation for boundary conditions. As per equal to 0 is nothing but its applied force is 0. And we have to sometimes take the boundary condition. Let us suppose that in a bar having applied, we have applied 10 newton or 5 kilonewton force will be there. That kind of things are boundary condition, nothing but. And also similarly we have seen the fluid mechanics, Poisson's flow pipe, how much flow in the fluids in a pipe, that kind of equation will be there. And similarly we got the thermal equation, diffusion and electrical conduction is there. And after making this governing equation, we have add with the boundary condition, then we got the finite element equations, that is in form of system of equations. And basically in this system of equation, there is the two terms, that is the stiffness matrix and nodal vectors and force vector is there. Force vector is nothing but applied force, which what amount of force applied in the system, and u is the nodal vector. Nodal vector nothing but it is the displacement at a node of element. We have similarly know that one element have containing two different nodes, and it's depend on types of element and it size of the element. We have let's here only talk with 1D element, that is a single line, in which line have a two number of nodes. And similarly we have a stiffness matrix to solve this, making these equations. Before after making the these equation, we have some procedures to solve the finite element equation. In the procedure, we have first select the field variable and element size, and that is also known as the discretization. Let us suppose that we have a one solid rod is there, and that rod is divided into some different kinds of element, that some different parts, that is known as discretization is there. And after discretization, we have select displacement function, that is u1 and u2. And after this selecting the displacement function, we have defined the relationship, what kind of relationship is there, just like a strain displacement or stress strain relationship is there. After defining the relationship, we have derived the stiffness matrix, that in form of equation. And we have making the stiffness matrix for one element to one element. Similarly, after making the one element stiffness matrix, we assemble or combine all the stiffness matrix is one matrix, that is known as global matrix or total matrix equation is there. On after applying the total equation or making the global stiffness matrix, we have applying the boundary condition, like fixed support is where, fixed support where is the free support, where kind of different kinds of loading is there. And after that we have seen the solved unknown the degree of freedom, we have knows then, if there is a number of n number of equation and n number of unknown variable is there, then we can easily solve. And with n plus one number of variable is there, then we not solve, we make as a finite element to solve that kind of problem. And first after that we have seen the element, what kind of strain and stress is there. And after making the taking the results of stress and strain, we interpret the that result in terms of analytical methods. This is whole analytical method to solve the finite element methods. We have seen procedure take by one example of a one d bar element. In that we have seen the two different diameter of a bar taking as a1 a2 and with the length of l1 and l2, that bar is fixed at the opposite ends. Similarly, we have engineering problem. Let us behavior find out the behavior of whole structure, and there is a one force applied at the mid of the surface, that is 7 kilonewton. We have seen next paragraph. And after that, taking this problem, we have similarly follow the steps. Discretization is nothing but making a element wise. Just here we have seen taking two elements. In this two element we have three different nodes, 1 and 2 and 3. 1 2 and 3, this is the nodes, and one element 1 and element 2 is there. For that discretizations, finite element getting number of nodes, and the choosing this most appropriate element type model most closely and actual physical behavior. So we have such where changed large element as where use result or relative constant is there. Some constant like young modulus, we have tank constant is there. After the discretization, we have follow the some select the displacement function of one element at let us suppose that we have a displacement function. It defines the element using nodal value of element that gives the value of field variable within the element. It may be of different kinds of element, linear, quadratic and cubic. Similarly, we have seen this is a linear element, so we have only two number of nodes, but they if there is a quadratic or other cubic polynomial or element will be there, then we have getting more number of nodes in one element. Are frequently function because they has a simple work to finite element formulation to find out this nodal displacement a1 as a constant and a2 and x is there. Similarly, after defining the displacement function, we have go to the defining the strain, displacement and stress relationship for the nodes. Just like a strain is equals to change in internal energy, change in displacement upon with respect to x. Similarly, stress is young modulus to the strain. That's making the relationship stress and strain. After taking the relationship, we have go for the stiffness matrix for the both of the element. Similarly, we have getting stiffness matrix of first element a1 e1 upon l1, having a matrix of in form of matrix in 1 1 minus 1 0 minus 1 1 0 0 0 0. In that we have seen z along the z direction is all the direction is 0. Similarly, in that is, let us suppose that 1 2 we have taking 1 and 2, 3 is 0. That's why all the row and column element of row is 0, and element 1 nodes 1 and 2 have some displacement. That's take the signature sign with their signs. And similarly we get the stiffness matrix for element 2. After this element stiffness matrix, we have add these two matrix that form the global matrix, global stiffness matrix, that is nothing but k is equals to k1 plus k2. We have knows that how to add this stiffness matrix. We have seen that we have get k is equals to over of global quad global stiffness matrix. Similarly, let us suppose that we have a one example. A1 is 100 mm square, E1 is the 200 gigapascal, L1 is the 200 mm is there. Similarly, we have A2, E2 and L2 is there. Then we have find A1 E1 upon L1 is this, and similarly A2 E2 upon L2 is equals to 40,000. After that we have put the final is finite element equation, that is f1 f2 f3 is there, and there is the matrix global stiffness matrix. After putting this value, we have getting the global stiffness matrix, and displacement function is there. Similarly, we have seen the here in the equation we have getting 120. After formation of the global matrix global equation, we have applying the boundary conditions. In the given figure, we have seen the element node 1 and node 3 are the fixed, then there is no displacement, then that's the reason u1 and u3 is equal to 0, whereas f2 is taking as force of 7000 newton. Let us suppose that here we have assumed that f2 is the force which I have value of 7000 newton. Then we have seen that above the equation we have three equation and three unknown is there, f1 f3 and u2. We can know that we have number of equation will be there, then we have easily find u2 value, that is displacement of u2 is 0.05 mm is there. Similarly, we have get u2 value, and now we have get find out the what is the f1 and f3 force in f1 and f3. We have finding this value from the calculation solving the equations, and now the making the relation which I have derived during the first time. We have a sigma 1 is 50 megapascal, and similarly we have sigma 2 is there minus 40 megapascal. That's all the stress in both bar. Now we have demonstrated this axial bar in Ansys Workbench in next module. Thank you everyone for watching this video. Have a good day.